Review one of the derivations we did before. Let's just look at this Feynman propagator. And what I will try to calculate is this one. Let me just use one of them as x. What is this thing? Well, in general, this is this one. But then there's the additional term. Because the time derivative, you cannot just put the time derivative inside the time-ordered product. There will be some extra terms over there. Why? Because the time-ordered product involves time explicitly in the step functions. So you have to take the derivative of the step function also, not just the fields. So let me just look at what the time derivatives are. This is the time derivative of theta x0 minus x20, phi of x, phi of x2, plus time derivative of x20 minus x0, phi of x2, phi of x. I just use the definition of the time-ordered product. Now let me take the derivatives. This will be the derivative of the step function is a Dirac delta function. So this is the first term will be the Dirac delta of x0 minus x20 of phi of x, phi of x2. Let me take the derivative of the second step function. That will be minus the Dirac delta of x20 minus x0. Phi of x2, phi of x. And then I have derivative of phi of x, but that is nothing but the time-ordered product of the t of phi of x, phi of x2. And this will give me Dirac delta x0 minus x20, the commutator of phi of x and phi of x2.
I missed the step that how we get the partial t from Laplacian.
I did not. I'm just looking at the time derivative of this expression.
Okay.
Because I know that here in the Laplacian I have the second time derivative acting on that time-ordered product. I'm just trying to figure out how that second time derivative acts on the time-ordered product. So I just calculated the first derivative.
What first derivative and where is the second derivative there?
Now I will calculate the second derivative.
Okay. We just write that it's separate.
Yeah. Now, that commutator is an equal time commutator. So fields at different points just commute with each other at equal times. So that commutator is just Dirac delta x. Well, in fact, sorry. That is just 0. This whole thing is 0. First of all, the commutators at equal times, so two fields at equal times, they always commute. So what I have shown here is the time derivative of this time-ordered product is just
isn't there also be a time-ordered product of phi x dt, phi x2 in the above?
You mean this one?
Yeah.
x2, no, I'm not taking, x2 is a different variable. It doesn't depend on t.
Doesn't that have the same time dependence?
No. It has, you see, I'm taking derivative with respect to the time of this one only. One is at time t, the other one is at time t2. It's a different variable.
This is zero. It's just, for example, the first drag delta just ensures that it's in the commutation is in equal time commutation, but it's already equal time.
No, it's not already equal time. You see,
Oh.
x is at x0, x is at t, x2 is at t2. One is at time t, the other one is at t2. So if x and x2 if t and t2 are different, then that commutator is non-zero, but the Dirac delta is zero.
Okay.
If t is equal to t2, or x0 is equal to x2 0, then that commutator is zero, the Dirac delta is whatever it is. Now I will take the second derivative. Well, you see, what I had shown up to here is, in fact, if you have a time derivative of a time-ordered product, you get the equal time commutator in addition to what you would get if the time ordering was not there. That is what I will use. I will skip some steps because this is equal to now dt. I took the first derivative. Now the second derivative would just give me the equal time commutator.
They vanish.
No. Plus, just move the derivative inside. I have another equal time commutator, but remember that time derivative is the momentum. It's not the field itself, it's the conjugate momentum to the field. So that commutator at equal times, this whole thing would give me Dirac delta x0 minus x2 0. The commutator of the momentum with coordinate is minus I times Dirac delta cubed, or minus R2. Momentum and coordinate, generalized coordinate and corresponding generalized momentum, their commutator will just give me that Dirac delta function, three-dimensional Dirac delta function. So I end up having del T squared is equal to minus I, the four-dimensional Dirac delta.
Because we are working with the position, there is no any 2 pi term there, right?
Yeah.
Because
The main norm of the empty state is just 1. And then plus I have this term. So what does this lead to? Well, this operator plus m squared acting on this time-ordered product is actually equal to, well, in fact, I don't even need this matrix element. This is equal to time-ordered product. I just move that operator inside the time ordering. But then I have this extra term.
why we did not calculate the special derivative of that? We look at the time derivative.
Because the time ordered product has a complicated time dependence. It doesn't. The time ordered product doesn't care about the position. Del I squared, the time ordering, is just in the definition of time ordering, I have these step functions that depend on time. And so when I'm taking the time derivative, I should also consider the time derivative of those step functions. But those step functions do not depend on position. They only depend on time. So that is why I have to treat the time derivative separately. But keep in mind that although time appears explicitly, it is still Lorentz invariant.
LSC formula we take outside the Langolin exposition.
I'm not talking about the LHZ formula here. I will not be connecting.
We should at the same time term make it fine. So in that formula we should also calculate this additional Dirac delta.
We already did. We did it over there. This is the relation I have. Now we can generalize it to more than two fields. Let's say, what happens if we have this one? Well, I mean, again, let's do this explicitly. Now, for simplicity, I will assume x2 0 is larger than x3 0. So x2 and x3, they are already time ordered. I mean, if they are not time ordered, just exchange their position and they will be time ordered. And I cannot assume that x0 is larger than them or not because I will be taking the derivatives with respect to t. So that is what I will keep. x0 or t can be larger than x2, equal to x2, smaller than x2, and similarly for x3. But what are the options I have? It can be that x0 is larger than x2, 0. Then I have phi of x, phi of x2, phi of x3. Or x2, 0 is larger than x0, but at the same time x0 is larger than x3, 0. Then it just comes in between. Or x3, 0 is larger than x0. It comes at the end. Since x2, 0, I assume x2, 0 is larger than x3, 0, these are the only three places that x can be. Either the latest, in between, or the earliest. Now let's take derivatives. This will be equal to, well, let me just write the Dirac deltas. In the second one, I have the derivative of the first Dirac delta, which will give me minus Dirac delta x0 minus x2, 0. Or plus Dirac delta x0 minus x3, 0. Plus the last one, or minus Then of course I have the derivative of phi itself, but those terms are nothing but the definition of the time-ordered product of derivative of the field phi and phi of x2, phi of x3. So this is the first derivative. Let me try to simplify this.
Why the minus term? How they come?
Minus 1. Minus 2.
Minus delta x0 minus x2 to the minus. Yeah. Ah.
It's just the derivative of the step function.
Yeah. Inside.
Now the derivative is the Dirac delta of whatever argument it has, but then you have to also multiply with the derivative of the argument. That brings you minus 1 signs.
Sorry.
Or you can think of it whether the step function is increasing as we increase t or decreasing to 0 as we increase t. It jumps up or down. Okay, now let me collect some of the terms. I have terms proportional to x0 minus x20. It is the first term and the second term. Remember, if you look at this term over here, I get, if I substitute instead of x0, x20, I get the step function of x20 minus x30, but I assume that x20 is larger than x30, so that's already 1. So I have phi of x, phi of x2 commutator, phi of x3. These are the first two lines. Then I have terms proportional to Dirac delta x0 minus x30. And again, if you look at this term over here, that step function, if I use the Dirac delta, that step function becomes x20 minus x30. Again, that is 1 by my initial assumption over here. So I end up having phi of x2 commutator of phi of x and phi of x3 plus time ordered product So again, you see what happens. If you take the time derivative of this time-ordered product, well, x and x2, in a sense, you can just think of it as x and x2, I get x, the commutator of x and x2, equal time commutator of x and x2, and x3, whatever that is. And then I get the equal time commutators of x and x3, equal time commutators with whatever remains. And then I get the time-ordered product of the derivative just moved inside. So these observations will help me when I'm generalizing to more than 3 fields. So if I had, for example, an arbitrary number of fields multiplying phi of x, what I would have obtained is I would just consider the equal time commutators of phi of x with each one of the other fields multiplying phi, and then the remaining terms. So this is what I have here. I get the equal time commutators of these two, then whatever remains. And then I have equal time commutators of phi of x and phi of x3, then whatever remains. If I had x4, I will get the equal time commutators of phi of x and phi of x4 times whatever remains. Or in general, I can say that del t, time-ordered product of phi of x, phi of x2, phi of xn is actually time-ordered product of del t of phi of x, phi of x2, phi of xn, plus Dirac delta x0 minus xn0, no, xj0, sum over all j times time-ordered product of phi of x2, phi of xj minus 1, phi of x j plus 1 phi of xn. Well, where is the time-ordered product in my derivation here? Well, I already assumed x2 and x3, they are time-ordered. So whether I put them in the time ordering or not doesn't really matter. So this will be the general expression. Now let me do another differentiation. Sorry, here I have commutator of phi of x with phi of xj. It's these commutators.
Right.
Well, equal time commutators of two fields is just 0. And so that second line is basically 0. Let me do the second derivative. Well, this is the derivative of the first derivative. The first derivative is just this thing. Because equal time commutators of two fields is just 0. I didn't write it down. Well, if I take one more derivative, this is the time-ordered product of del t squared phi of x, phi of xn, plus sum over all fields.
We didn't write the second term, right?
The second term is 0 in the first
Yeah,
derivative.
okay.
That's why I didn't
I
write
was
it.
wondering.
Now I have to write it down because it's not 0. Because now I get the commutator of del t phi of x with phi of xj times the time-ordered product of phi of x2, phi of xj minus 1. You just jump xj. But that commutator is just minus I, the three-dimensional Dirac delta of x minus xj. So this del t squared of this time-ordered product is equal to the time-ordered product of the second time derivative of this field phi of x times minus I, sum over all the fields I have, Dirac delta 4 x minus xj, the four-dimensional Dirac delta. Well, there is 1 because of the Dirac delta of time. There are 3 more because of the momentum coordinate commutation relationship. And I have time ordered of phi of x2, phi of xj minus 1, now in particular, now I can just act with this thing on my time ordered product. Let's even say the time ordered matrix element of that time ordered product. This is the matrix element in the full theory. This will be equal to acting on phi of x minus I This is called the Schwinger-Dyson equation. Now, what is the use of it? Well, you see, here I have an endpoint function that I will be interested in calculating the scattering of particles, for example, in the full theory. This is an n-2 point function. I'm relating endpoint function to n-2 point function plus interactions. This is where the interactions will come from. Why? Well, let's say that I am looking for L is equal to 1 over 2 del mu phi squared minus m squared over 2 of phi squared plus, let's say, some interaction terms, whatever they are. What are the equations of motion? Well, del mu, derivative of the Lagrangian with respect to del mu phi minus derivative of the Lagrangian with respect to phi, this is equal to 0. Well, the first term will give me del mu times del mu phi. The second term will give me plus m squared phi plus or minus derivative of the interaction Lagrangian. But I will be assuming it depends only on phi. Or plus m squared phi should be equal to the derivative of the interaction Lagrangian. So this was the equation I have. This is just my interaction Lagrangian derivative. So here on the left-hand side, I have my n-point function. On the right-hand side, I have an n-2 point function. And here, this is whatever, it depends on what my interaction Lagrangian is.
So we somehow get rid of the phi s, and our equation decreased to n-1 function.
Well, you see, here I still have phi x. So I didn't really get rid of phi of x. But you see, that first term is one higher order in the interaction. It contains an extra interaction Lagrangian. That is what we will be using in a moment. And the nice thing is, you see, we have the Wick theorem, which allows us to calculate the matrix elements in the non-interacting theory. But now this is an identity in the fully interacting theory. This is valid for the full theory for the exact endpoint functions. It just relates different endpoint functions to each other. Well, of course, in that form, since I have many sums over there, let's say if L interaction were absent, in the free case, let's say, this would allow me to relate the endpoint function to the n-2 point function, and then I can use a similar equation relating n-2 point function to the n-4 point function, etc., until I get a 0 point function, which is just 1. If there are interactions, usually L prime will involve more than second power of phi. Let's say it will involve phi cubed. Then its derivative is phi squared. So this is an n+1 point function. So I have an n point function. I relate it to an n+1 point function and an n-2 point function. In that case, I have an infinite tower. So it's not that useful in that form. But still, it's an exact relation we have for the exact theory, full theory. Now let's apply this. Now we can use this to derive the Feynman rules we have. Now let's start with the 2-point function. of the full theory? Well, we can use the Feynman rules that we had already derived. Let me also look at the theory with L interaction is equal to lambda over 4 factorial phi to the 4. Well, the diagrams I have will be this
Is there a
one,
special name for this interaction? Phi 4.
phi to the 4.
I've seen everywhere that.
Yeah, we will discuss why we only look at phi to the 4 next term. Plus, I have this term, plus I have this term, even higher orders, plus I have this term. This term is of the order of lambda. These two are of the order of lambda squared. There are two interaction potentials. Plus I have all higher order terms. This we already know from our earlier discussion about the Feynman diagrams using the Wick theorem. Now, let me do an alternative derivation. Remember, we also derived the Feynman propagator. If I act on my Feynman propagator with this operator, I will get minus I Dirac delta, 4-dimensional Dirac delta x. So this is equal to d4x Dirac delta x, 4-dimensional Dirac delta, time ordered product of phi of x2 I can evaluate the d4x using the Dirac delta, and that's just an identity. But now I can just replace this Dirac delta x with I times this operator acting on my Feynman propagator. Sorry. X minus x1. I want the x to become x1. So this is the Feynman propagator at x1 minus x1. This is equal to I d4x. This is the derivative with respect to x. Now I can do integration by parts and move all that operators in my D'Alembertian into acting on the matrix element. I have to do integration by part twice. I will ignore the boundary terms. This is equal to I d4x. Now I know how that operator acts on the matrix element of time ordered product. Remember, this is the expression I have. Well, in the first term, what appears is just replace phi by the derivative of the interaction Lagrangian. Well, the derivative of the interaction Lagrangian, remember this is my interaction Lagrangian, so it's lambda over 3 factorial phi cubed at x phi of x2. This is the first term. Then I have the Dirac delta part. It's just, it tells me that I should remove phi of x and another field appearing in multiplying phi of x, take the 4-dimensional Dirac delta of those two fields, and just write whatever remains inside the time ordered product, but here there is nothing remains. So this is minus I times the 4-dimensional Dirac delta of x minus x2. So what I obtain is this matrix element is equal to, well, if I just write this term, this is equal to, I can integrate over the x using that Dirac delta. It just gives me the f x2 minus x1. Then I have plus I d4x dfx minus x1 lambda over 3 factorial matrix element of phi cubed x phi of x2. So especially if I'm interested in the expression at lambda is equal to 0, the second term is not there. This is just the Feynman propagator we defined. Now I can repeat this process. Let me just repeat it by saying that this is the f x2 minus x1 plus I lambda over 3 factorial. I have d4x x minus x1. Let me introduce a Dirac delta over y. Integrating over y will just give me 1. So I'm not actually doing anything. Phi of y, phi squared of x, phi of x2. No. I mean, I have phi cubed x. That's the product of 3 phi x's. I'm just replacing one of them with y. And if you just integrate over y, I didn't change anything. Yeah. Well, I will again do the same trick. This is nothing but, no, not that one. This is I times, this time with respect to y, of this thing acting on my Feynman propagator x minus y. So what do I get? The f x2 minus x1. Again, I will do integration by parts with respect to y. That will give me plus I lambda over 3 factorial. There's another I, this I. Then I have d4x, d4y, dfx minus x1, dfx minus y, and this operator acting on this time ordering. Now I know how to act with that operator on that time ordering. Well, what does Schwinger-Dyson equation tell me? First, just move that operator inside, remove phi of y, and replace it with the derivative of the Lagrange, interaction Lagrangian. So I get lambda over 3 factorial phi cubed evaluated at y. Then I have phi squared x, phi of x2. Omega. I remember now, note that this is lambda squared now. There is one lambda over here. This term is now a correction at the lambda squared order. But then I have to add minus I times the Dirac delta terms, well, phi of y can commute with 1 of the phi of x. What I will get is whatever remains but then phi of y should also commute with the other phi of x, so there is that factor too. And then phi of y can commute with minus I with x2. Squared. These are all the terms I have. So let me write it explicitly. This is equal to df x2 minus x1 plus I lambda over 3 factorial I d4x d4y dfx minus x1 dfx minus y times omega time ordered product, or let me write it in this way, this thing squared, because there's another lambda over 3 factorial here, phi cubed y phi squared x phi of x2. Then I have plus 2I lambda over 3 factorial times 2, I'm just writing this term. Remember, there's an I over here, a minus I over here, so I just cancel them. I lambda over 3 factorial times 2 times, now I can integrate over, let's say, y. If I integrate over y, what I have, x remains. Let me integrate over, x remains, d4x, d4x minus x1, dfx minus x. This is this one. And I have this term. Then there's a contribution from this one, which will be plus I lambda over 3 factorial. I will integrate again over y. This Dirac delta tells me that instead of y, I should put x2. I have d4x dfx minus x1 dfx minus x2, and I have omega t omega. Okay, up to now, everything is exact. On the left-hand side, I'm calculating this exact two-point function on the left-hand side. On the right-hand side, I also have, okay, this is the Feynman propagator I have. This is an exact 6-point function. This is an exact 2-point function. And this is an exact 2-point function. So I'm looking for, this is a relation that relates exact 2-point functions and exact 6-point functions. Now let's say that up to and including corrections of the order of lambda. This is this propagator, this term. Well, this term is lambda squared over 3 factorial. Now, if you look at this term, you see this is the 2-point function, but it is multiplied by lambda already. So here I should use the 2-point function of up to order lambda. So that will give me plus I lambda over 3 d4x df, this one of these should, df x minus x1, df x minus x, df x minus x2. The same thing over here. It is already multiplied by lambda, so if I'm interested in everything up to the first order in lambda, I should take the lambda to the 0 term in this expansion. Lambda to the 0 term in that expansion is just replace this by the fermion propagator, which is this term. I would have plus I lambda over 3 factorial d4x df x minus x1 df x minus x2 df x minus x, plus there will be terms of the order of lambda squared. Well, if you look at the diagrams, this is just the propagator connecting x1 and x2. In these ones, I have there is an intermediate point x. So this is x1, this is x2, this is x. x1 is connected to x, x2 is connected to x, and x is connected to itself. Well, these two terms are the same. So these are my diagrams. And if you look at the coefficient of this term, there is 1 over 3 here, plus 1 over 3 times 2. This is 3 over 3 times 2. 1 over 2, this is nothing but our symmetry factor that we calculated before. So we basically get this same, exactly same expression. Now, this is more tedious than what we did before. But the one advantage this has is it is exact. You see, this relation over here is exact. So that relation, if you can make sense out of it, you can also use in theories where perturbation theory doesn't work. Of course, there is a problem of what sense can you make out of that. That still remains. But this is valid also in non-perturbative theories. What we had done before was basically obtaining the perturbative expansion. We cannot really use it if perturbation doesn't work. Why doesn't it work? Well, you end up having theories in which higher contributions become larger and larger. So you have to come up with other tricks to deal with them.
Is this the standard way of writing the Schwinger-Dyson equation, by the way?
I don't know.
That's not how I've seen it though. It looks like I thought it looked like a Euler-Lagrange, generalized Euler-Lagrange. That's what it was.
Well, I like this one.
I've never seen it like this.
No, I mean, it's tedious,
Yeah.
but it's kind of straightforward. This is from Schwartz.
Ah,
Hmm?
same.
Any questions? Not too tired. Okay, there is one more topic left to discuss. What happens if we have derivatives in the interactions? So that is what we will discuss on Thursday, and hopefully then start spin 1 particles.
No path integrals? Are we not doing them in this course?
Not this term,
Okay.
maybe next term.
Excuse me, what did you ask? What?
Path integrals. Path integration.
Path integral quantization. I mean, this semester will be mainly the basics. We have been discussing the scalar fields. Then we have the spin 1, the vector fields. And then we should also discuss the spinors. So that will basically give us everything we need to talk about quantum electrodynamics.
And
You haven't decided the date of the second midterm, right?
Not yet. I mean, we can discuss together.
Okay. Just wondered because I wasn't present.
No. I mean, let's say that this is the 8th week, right? 4 weeks from now.
Okay.
I mean, when the time arrives, we can shift it 1 day, 1 week after, 1 week before. But I mean, if we wait after the 12th week, then it will be the same as final, more or less.
Well, the final is very late, actually. The final date is out, you know that. The final is very late, 17th January. What topics do you want to do before the second midterm? What do you want to finish spin 1 before the second midterm? Is that the...
Yeah, I mean, I won't be doing all the details in Schwartz. Is it the Schwartz book is nice. I mean, for me, it's really great. There are all these missing parts that I'm missing in my understanding. It fills those parts